Hi again, we are still in lecture 2. Now we will learn already about metabolism, which is a sum of all chemical reaction in the organism. It's a balance between catabolism, the breaking down, and the building up anabolism. And living organisms use energy from their surrounding to maintain their structure, to build up some new compounds, to use as cellular energy to do mechanical works, to do many works, and energy in biological system is ATP, and we obtain ATP by catabolic reaction, breaking down of macromolecules to smaller molecules, and we use ATP as an energy in anabolism, which is building up the bigger molecules. Now, let's move on to the next topic, which is how do we know when the reaction will occur? In general, chemical reaction is a rearrangement of chemical structures into a form to form a new chemical molecules. The energy in the reaction is represented by delta G, which is the free energy. It's equal to the energy of the products. Here is our chemical reaction. A plus B, those A and B are reactants. And after the reaction occurs, you get products P and Q. The energy of the reaction is the energy of the products, delta G of P plus Q, minus the delta G, the free energy of the reactant A and B. So the reaction, the delta G of the reaction is equal to the delta G, the energy of the products, minus the energy of the reactant. And we can categorize the chemical reaction into two bases on whether it can happen spontaneously or not. The first one is the chemical reaction that cannot occur spontaneously. We call this reaction endogenic reaction. It is the reaction that needs an energy to proceed. Basically, the free energy, look at this diagram. On the y-axis, you have free energy, the delta G. The x-axis, you have the progress of the reaction. At the beginning, you have the reactant A and B, which has the delta G or the energy at some point. And look at the products. Once the times go by, you have P and Q as the products, but their free energy is even higher than their reactant. So by using this equation, you have more of the products, of the energy in the products, and you have less energy of the reactant. When you put this and do math, you get the delta G of the reaction in the positive side. This means this reaction needs energy from the reactant to go up to the level of the products. You need an input energy. So if you don't do anything, you don't add energy, this reaction will not happen. So it's called non-spontaneous reaction or endogenic reaction. On the other hand, if the reaction can proceed, I forgot to add this one. So this is the differences between the PQ, the products, and the reactant A plus B. So you need energy. So the second type of reaction is endogenic reaction, which is the system that you have lower energy of the products compared to the reactant. When you do math in this equation, the product has lower energy, and then we subtract it with the higher energy of the reactant, you get the negative values of the delta G of the reaction. This means that your reaction is actually release some energy to the environment. It do not need any energy. It can happen just by sitting around, and it even give the products of energy. It even give the energy to the environment, so it can occur spontaneously, and we call it exergonic reaction. All right. So we talk about the beginning, the reactant, and the products. We didn't talk about what happens in the middle, and it's actually happened like this. All the reaction is not actually consider only the start point and the end point, but we need to consider what happened in the middle. You can see that the level of energy of something in the middle is even higher than everything else in the process. So what in the middle right here, what happens? It's called transition state. And what is transition state? It's actually the state that is not stable. It happens because when you need something to happen, you need to break the bond of the reactant first. The molecules contains atoms, and atoms form bonds together in A and B reactant inside their molecules. Those bonds need to be bent, needs to be distorted, needs to be deformed, need to change. So the energy that required to bend the bonds is even greater than anything else to get into this transition state. So if you take a look at this reaction, A plus B, it need to have the transition state. You have X with the double plus sign right here, and then you get the products. So let's take a look. For example, A molecules has this structure and B looks like this, and your products P look like this. You can see that now you have the yellow dot with the dark purple, not dark purple, dark blue, and green from the B. And you have shuffle the light blue with another green molecules, or the atoms, for example. So you have changed from reactant to the products. But during the middle, you need to break this bond and reshuffle everything again. By breaking this bond, you need a lot of energy to get into this transition state. And this energy, we call it activation energy. So this is for the last slide, we know about delta G of the reaction, which is equal to delta G of the products minus delta G of the reactant. If you take a look, this delta G of reaction didn't take an account of the transition state. It's considered only the beginning and the finish. So, but in the real situation, you need to take an account of the activation energy, which is can be calculated by the energy of the transition state minus the energy of the reactant, which are shown in this diagram. So it is the differences between the energy of transition state compared to the reactant. The higher the hue of the activation energy, the more difficult the reactant to get into this activation energy, or or to the transition state. And once the reactant become in the transition state, there is an equal chance, equal probability that the reaction will go toward the products or go back to the reactant. All right? This is the reason why the spontaneous reaction, like in this graph, when you consider the reactant has a higher energy compared to the lower energy of the product. It just cannot take place spontaneously. It also needs an energy to proceed because you need to consider the transition state, which require a lot more energy. All right. In general, if nothing happens, reaction will not occur very easily. It will take millions of seconds, not like that. It can take many years to happen. For example, if you want to break down the sucrose, the sugar that you eat, into glucose and fructose, it will take many years. But if you add a catalyst to the reaction, you can even lower the activation energy. You can lower the hue of the activation energy. So catalyst is actually a substance that can speed up the chemical reaction. It can reduce the activation energy and the reaction will go toward the products more easily. So this is the reaction coordinate of the uncatalyzed or no enzyme, no catalyst reaction, and the catalyzed reaction, the reaction with catalyst. You can see that the activation energy is lower. So what is the catalyst? What it can be? It can be some chemicals. It can be an acid, it can be basic, it can be heat, it can be pressure. But for biochemical system, like in our body, like in animals, like in your dog, like in your cat or fish, or like in bacteria, plants, or yeast, those extreme catalysts cannot be used because our biological system is so delicate. We cannot tolerate the high heat, high pressure, acid, or very strong basic. So we have adopt a new system. We have adopt a new tools, which is enzymes. We'll learn about the enzyme in just probably the next lecture in the real situation. But right here, enzyme is a biochemical catalyst. It's similar to other catalysts. It can enhance the speed of the reaction without being consumed by the process. It's just like a helper. All right. And so if you consider the catalyst, it can just speed up the reaction, but the delta G of the reaction are still the same. Your energy of the products are the same, and the energy of the reactant, the end point and the start point are still the same. So the delta G of the reaction is still the same. What changed is the delta G of the transition state. It will be lower. The activation energy is lower. All right, now we will focus about the enzyme, how it works. Enzyme is actually providing a specific environment to help the reaction to proceed more rapidly. The catalytic reaction can take place in a pocket of an enzyme. We call it active site. The molecules that bind to the active site of an enzyme is called substrate. We have at least two models so far. We have lock and key model. It's just like you have an active site as a lock, and the substrate is like a key. And when two things combine together like a jigsaw, it will become an enzyme substrate complex. Another model is an induced fit hypothesis. Actually, the active site and the substrate, without forming a bond together, their shape are not fit perfectly. But once they draw together to each other, they will fit together perfectly, or the space between the two will be eliminated and will become an enzyme substrate complex. So now I told you that an enzyme and substrate can form together. And actually I forget one thing. So substrate in this case is actually, if you compare this to the normal chemical reaction, is actually the reactant. So in biological system or biological reaction, we call reactant that need an enzyme as a catalyst as the substrate. So reactant and substrate are the same, but not exactly the same. Substrate is for biological reaction that need an enzyme as a catalyst. So let's take a look at this diagram. So in total, I just want to tell you that an enzyme cannot fit perfectly with the substrate. It would not help speeding up the reaction, but it need to fit perfectly with the transition state in order to speed up the reaction. What happens? Let's take a look. So if you have a reaction by breaking a magnetized metal stick, breaking it down into two pieces, in order to make the products two pieces of metal stick, first you need to have the metal stick bended. So the bent metal stick is represent the transition state. Without any catalyst, let's take a look at reaction coordinate. You have the transition state and the activation energy this much. With an enzyme that complement to the substrate perfectly, the enzyme is actually has the magnet that can stick to the magnetized metal stick very well. And if an enzyme fit perfectly with the metal stick, it will stabilize the metal stick and it will not allow the metal stick to bend. And so we will not get the products anyway. If you take a look at the reaction coordinate, an enzyme will lower the substrate or the reactant, lower the energy of it. So instead of starting from the higher energy substrate and then get into the transition state with this much of activation energy, once the enzyme lower the energy of the substrate, your activation energy, the blue lines right here, will be longer than without the catalyst of activation energy. So in this case, your enzyme is useless. It impede the reaction. Your reaction will go slower than without an enzyme. So this is even the worst case. But if your enzyme is not fit very well with the substrate, but actually is fit more perfectly with the transition state, which is the bent metal stick, you will get the product more easily. The reaction will speed faster. if you take a look at the reaction coordinate, you will lower the activation energy. Let's take a look at this arrow. You have lower activation energy compared to the non-catalyst reaction. So the reaction will proceed more easily. Alright, so the bottom line is the enzyme need to complement to the transition state, but not to the substrate. Alright, so how the enzymes works. I told you earlier an enzyme need to fit with the transition state, but how it help? It will provide a more comfortable fit with the transition state. It will bind to the transition state, and the binding of the enzyme to the transition state occurs spontaneously. Is an exergonic reaction, is releasing the energy, and the energy of the binding, once it released, is help reducing the activation energy. For example, this sucrose need to be combust into carbon dioxide. This energy is exergonic with our catalyst, but you can see that if you put the table sugar in a jar, it will not go away. It will not combust into carbon dioxide in your lifetime. But you need a catalyst to speed up this reaction. Once you add an enzyme sucrase that we will learn again in the lab too, this reaction will happen in seconds. Alright? So an enzyme is just speeding up the reaction, but not changing the delta G of the reaction. So now I want you guys to focus more on the reaction rate. I think I already mentioned it a lot. So enzyme substrate, and then you get the products. And enzyme, you get an enzyme because an enzyme is not being consumed. And equilibrium is a direction of the reaction, and enzyme will not determine the direction or equilibrium of the reaction. What's determined is the delta G. If it's the negative, that means it will occur spontaneously to the products. But if it's above the zero, if it's positive, it will prefer to be the substrate. All right? And the rate of the reaction is determined by an enzymes, but not equilibrium. All right? Just take a look at the graph. And this one is the spontaneous reaction because your product has lower energy. And before we go to more detail about an enzyme, I want you guys to know a few more things. The reaction intermediates like enzyme substrate and enzyme products. They are transient chemical species, very short term of actual chemical, very transient. They have a very short life. They will form very quick and they will decay very quickly. And it can, in the reaction, biochemical reaction, you can have many intermediates. You can have many steps. And the step that require the highest activation energy, you can have a lot of bumps, and a bumps that has the highest hill, bigger hill, we call that rate limiting step. For this picture, you have three peaks, three hill, and this one is the highest of the activation energy. We call this step is the rate limiting step. All right, we'll stop right here and we'll come back with more of the enzymes. See you in the next video.